This is Jack Jackson. We're going to take a look today at exploring some structure of linear and exponential functions, particularly arithmetic and geometric sequences. And we're going to kind of focus our attention on this project that we had worked on earlier. And if you remember, in the project, we had a certain number of blocks, and we had a couple of different scenarios we were looking at. The first scenario was where we started with a certain number of blocks, let's say 7 blocks, and then each stage or each step we were to add 2 blocks to our collection of blocks and keep track of how many blocks we had total. So we're repeatedly adding 2. Started with 7, added 2 to got 9, add 2 more, get 11, and so forth. Well, as we looked at this earlier, this leads to an arithmetic sequence, or in turn that leads to a linear function. But we also had another setup, and that setup was where we maybe started with 7 blocks, but this time instead of adding 2 to the previous number of blocks, we multiplied the number of blocks in the previous step by 2 to get the number of blocks in the next step. So we just doubled the number of blocks. So we started with 7, then we went to 14, then 28, and so forth. Well, this leads to another kind of sequence called geometric sequence. So if you haven't done this project, or if it's been a while, you might want to go back to it. It's posted up above this video in Blackboard, and what you can do is look at that project and maybe at least open it up and refresh your memory. Hopefully you did this project back in Unit 2 or earlier unit when we were working on linear functions, but now we're going to go back to the part of it that's exponential functions. We're going to review the linear part as well too. So here we go. So this particular sketch is set up so that I can illustrate this, and this is starting with 7 blocks. Y sub 0 is the amount we start with. I can change that if I want to in the sketch to 5 or like that or whatever. But let's say we start with 7, for example. And this is M is how much we add each time. It's the common difference, or how much we're adding each time to get the next one. So we're going to start with 7 blocks, add 2, then the next step we'll add 2. So notice the Y here in red is the total number of blocks, and the X is the step number. So if we're going to consider we're starting with the 0th step, then we're starting with 7 blocks. Okay? And if I go up a step, if you notice down here in the bottom left corner, you can see that we added 2 blocks for a total of 9. And now we're adding 2 more. This is one way we could snap the blocks together and arrange them. So now we have 11 blocks, and then add 2 more, and 2 more, and 2 more, and so forth. And you can see it's going up by 2 each time. Now if we keep track of these numbers of blocks in a table here, you can see it in the table. So again, we're starting with the 0th step with 7 blocks, and every time we add 1 to X, add 1 to our step number, we're adding 2 to the number of blocks. And so we can see these numbers in the table here. Okay? So we have a nice little pattern. Well, how did we get from 7 to 9? Well, we just added 2. So we have a nice little recursive pattern. We start with 7. To get 9, we get 7 plus 2. To get 11, we get 9 plus 2. And then that gives us 11. And then once we add 2 to that, we get 13, and so forth. So we have a recursive formula that says, well, the 0th step has 7 blocks, and then f of x equals f of x minus 1 plus m. So this m is the common difference, or delta y, when delta x is 1. And of course we also know that's a slope. Then we also noticed this before, that we could rewrite this as 7 for the 0th step, then 7 plus 2 for the next, then 7 plus 2 plus another 2 for the next one, and 7 plus 2 plus 2 plus another 2, and so on forever. And so really we can view every single y value here as just our original 7 blocks plus a certain number of 2's. Well, so it's just 7 plus a bunch of 2's. Well, how many 2's? And how can we rewrite this? Well, one nice thing is we have a shorthand notation for repeatedly adding the same thing over and over again, and of course that's multiplication. And so we see that what we're doing here is we're multiplying the 2 by some number and adding to 7. So we're starting with the 7, then we're adding to that a certain number of 2's. The number in the parentheses counts how many 2's we added. And there's our repeated addition, which is multiplication. It also turns out that the number in parentheses is the step number So this allows us to get an explicit formula that says y equals 2x plus 7. So in general, this is y equals mx plus y sub 0. If I change the value of y, let's say instead of 7, but change it to 4, that's going to change that initial value, and that's going to change the constant term here, which is our y sub 0. Of course, 0, 4 is the y-intercept, so that is y of 0. Notice if you plug in, it doesn't really matter what m is. M times 0 is 0 plus y sub 0 is y sub 0. So this definitely has the point 0, y sub 0 on it, which is, of course, when you graph a y-intercept. If I change the value of m, let's say to 3, now we're going up by 3's each time, and that changes that coefficient. Okay? Now keep that in mind, and we're going to go over here. Let's go back to our original one and just say it's 7, and then this is 2. So again, we're starting with 7, repeatedly adding 2. Keep that in mind. We're going to go over here to this example. And notice I've still got y sub 0 is 7, so I'm still starting with 7 blocks, which I've arranged vertically this time. But this time the base is 2, and the base, not m this time, but b, is 2. And what this does is this allows us to, tells us how many times we're going to multiply. So as I step through this, notice I first have 7 blocks. I'm going to just basically copy what I've got and add it on so that I'm doubling the total number of blocks. So now we're up to 14. And we double again, we're at 28. Double again, we're at 56. Double that whole thing again, 112, 224, 448, 896, and so on. So that as we go through this, it gets pretty big pretty quickly. Okay, let me step it back to the beginning. So at the when x is 0, we start with our 7 blocks. And then if we add 1 to x to make it the second step, we're actually going to multiply the y's by 2 to get 14. And you can see this, so forth. So that gives us a nice recursive pattern. Of course, you know what this is, right? We're just taking each x there, and we're multiplying. We're taking the x and adding 1 to it to get the next value. And if we want to find the y, we take the previous y and multiply by 2. So we could get the 14 by 7 times 2. You get 28 by taking the 14 times 2. Multiply, that's 28. Multiply that by 2 to get 56. Multiply that by 2 to get 112. So we're still adding 1 to get the next x, but now we're multiplying by 2. Notice over here in arithmetic sequences, we were adding 2 each time. So where what is addition here becomes multiplication over here. Now just as over here we could rewrite this as the first term and then just a bunch of 2's added, we can take this as the first term with a bunch of 2's multiplied. And so we see that we start with 7, then we have 7 times 2, then we take that 7 times 2 times another 2, and then 7 times 2 times 2 times another 2, and so forth. So we just get 7 times a whole bunch of 2's multiplied together. Well, over here we were able to, in arithmetic sequences, we were able to rewrite this repeated addition as multiplication. How can we rewrite repeated multiplication here? Well, repeated multiplication is actually what we mean by exponents or powers. So the part that we're multiplying over and over again is what we call the base. And then the exponent is how many times we're multiplying it together. And so we can think of this as 7 times, of course 2 to the 0 is 1, so 7 times 2 to the 0 is 7 times 1, which is 7. That's our starting point, and that still works even when x is 0. And then from there on, the exponent, the number in parentheses here, counts how many times we multiplied by 2. And so there we have it in a more compressed format. But then we also notice that the number in parentheses, the exponent, is actually the same as the step number x. So that allows us to come up with a explicit formula. Notice here in blue I already have a recursive formula that says to find one x, we go back to the previous x, x minus 1, find its y, f of x minus 1, and then multiply by b. So f of x equals f of x minus 1 times b. You take that along with some initial point, any one of these points actually, but say for example 0, 7, that's enough to describe what's going on here in the table. But with this formula over here, we can with this way of writing it over here, we could come up with a formula that's an explicit formula, and very similar to the one over here where we had the y-intercept, the y-coordinate of the y-intercept, and then the slope, it was a coefficient. So this is a slope y-intercept form, or usually just called the slope-intercept form. Over here we have instead of a slope, it's a base, and then y-intercept. So the 7 right here, I'm still going to call it y sub 0. That is the y-coordinate of the y-intercept when we graph it. That is the output when x is 0, as we see right here. Okay, it's our initial amount at x equals 0. And then the base here is how much we're multiplying each time. So, of course, the base is our common ratio. Over here we found our slope was our common difference. The slope was delta y, or y2 minus y1, and that works whenever delta x is 1. Over here in this case here, in the geometric sequences is what we call this, we're multiplying by 2 each time. So that 2 is the common ratio. That is, we are dividing a y2 divided by the 1y divided by the previous y. 14 divided by 7 is 2, so that means 2 times 7 is 14. 28 divided by 14 is 2, so that means 2 times 14 is 28. And every time when you divide successive y's here, you have a common ratio that it's always the same, and we call that, I'm going to call that b for the base. Now, just one word of caution, some books will call, this is the common ratio when we're talking about geometric sequence. It's often used, denoted as r for this. I try to avoid using the letter r here. I'd rather use the letter b for base, because I'd like to use the r for something else entirely, which is the relative rate of change, or the percentage rate of change. We'll get back to that a little bit as we get a little bit further into our next section, but I want you to, we're going to use the letter b, but you might see it used as a letter r in a textbook or something. Okay, so let's just review a couple of things here. I'm going to write down some handwritten notes here. So on the left hand we have an arithmetic sequence. On the right hand we have a geometric sequence. These are the two things we're looking at. So notice that we start with, we have an ordered pair 0, y0. Over here we have an ordered pair 0, y0. That's our initial amount. Okay, so far the same. And how do we get a new y? So if we want to do f of some x, recursively what we do is we back up 1 for the x, find its y, and add this common difference, which is m. Okay? Over here, how do we find maybe I'll use g over here, g of x. Okay? How do we find g of x over here? Well, what we did is we backed up to the previous x, found its g, but then we multiplied by the base. So notice what's multiplication here is what used to be addition over here. It's one level higher in the order of operations. So in other words, add the slope, m, which is the common difference, each time, a constant amount, to get the new y when you go up by 1. Over here we multiply by the base b, which is the common ratio, to get the next y. And this is when delta x is 1. So when delta x is 1, what is the slope? The slope is delta y, which is y2 minus y1. Over here, if delta x equals 1, okay, what's the base? It's the common ratio, y2 divided by y1. Look what's happening here. On the right side, on the geometric, we have multiplication where we used to have addition. We have division where we used to have subtraction. It's one level higher in the order of operations. Okay, let's continue on. We'll see this a little later. I'm going to go ahead and... what if m is not... what if delta x is not 1? We have to do an adjustment and say it's delta y divided by delta x. So that's the slope in general. So we're dividing, in other words, it's y2 minus y1, and then we divide by delta x. Okay, hopefully this will make some sense. We're going to derive this a little bit more carefully a little bit later on. But I do want to show you that we may have to make an adjustment here. Okay, well, just like we subtracted y2 minus y1 over here we're going to divide y2 divided by y1. Over here we divide by delta x, so over here we need a delta x root, or 1 over delta x power. So this is in general. So this slope is constant if and only if it is arithmetic. And this base is constant if and only if it is geometric. And so the basic formula then becomes y equals m x minus m. Let me write it. There's several forms actually, but one form we had is y equals mx plus y sub 0. And again, m is the slope, and so 0 y0 is the y-intercept, and m is the slope. So this is called a slope-intercept, or to be more specific, a slope y-intercept form. Well, similarly over here, our form is we have our base to the x power. Okay, and where this was addition, so we start with our y0. Where we add to it over here on arithmetic, over here we multiply. And over here we have repeated addition is multiplication. On the geometric, where we have repeated multiplication, it's an exponent. And again, 0, y0 is the y-intercept. Okay, and b is the base, which is our common ratio. Okay, it's what we're multiplying by each time if delta x is 1, whereas the slope is what we're adding each time. So you can kind of see a parallel here between arithmetic sequences and geometric sequences. In geometric sequences, what are we doing? We're basically doing the same thing as we did in arithmetic sequences, but we're pumping it up one level in the order of operations. Where we had, anytime we had addition in arithmetic, we now have multiplication in geometric. Anytime we had subtraction in the discussion of arithmetic sequences, we now have division in the discussion of geometric sequences. Anytime we had a multiplication in arithmetic, we now got a power in geometric. And everywhere we had division in arithmetic, we have a root or a fraction power over in the geometric. Okay? And of course, if we extend this to be domain to be in all reals, this is linear functions, and if we extend the domain to all reals over here, this is exponential. Okay, so let's go back to our sketch and continue with this a little bit more. So let's go back to arithmetic for just a minute. So now if we graph this, you can see that here it's a sequence of dots. The dots go to the right and up forever, but in this case you don't have anything below the 0th step, so it just stops there on the axis. But we do see the 0, 7 as this point right here on the x-axis. Okay, y-axis, excuse me. It's the y-intercept. Now this is thinking of this as a sequence. In this case we would call it an arithmetic sequence. An arithmetic sequence then, is, the inputs are just the step numbers, 0, 1, 2, 3. Natural numbers, or in this case I included a 0th term as well. Sometimes when we talk about sequences, we talk about starting with the first term, and sometimes we start talking about the 0th term. So I started as the 0th term here. But we can extend this now, even though this particular thing in terms of blocks doesn't make sense for a negative number of blocks or a fraction of blocks, we can extend this out to be y equals mx plus y sub 0, but where we allow any real number for x, and of course in this case we actually get all real numbers for y, so the domain and range are both all real numbers. And of course the graph is now a solid straight line. Okay, and of course that's a continuous function, and we have this setup, so we have a solid line. Okay, that's called a linear function, and it's named linear because of the graph. So we name linear functions after their graph. Let's go over here to geometric and see what happens. Well, it's definitely not going to be straight anymore. Let's see if you can kind of see what's happening here. Okay, let's just check some of the points here. We have 0, 7 right here. Then we have 1, 14, 2, 28. I definitely don't have a square scale here. This is only 2 on the x's, but we've already gone up to 14 on y. So I've definitely stretched out the scale. If I did it more on a scale, it would be more like this. But if you put it like this, you can see a little bit better. Now this is definitely not linear because the slopes are not the same. These points are not in a straight line. Of course, any 2 of them would be, but when you take 3 of them, there's not a line. There's a definite concavity here, and we can see a definite concave up shape. So we have positive slopes all the way around here, so it's always increasing, but it's increasing at an increasing rate as we go to the right, so it's curving up. Now again, this is for a number of blocks, it would just be these dots. They do go to the right and up forever. But if we were to connect these up and make a continuous function out of it, then we get the formula f of x equals y sub 0 times b to the x. But now what we're doing is we're letting any possible real number x work in this formula. And in fact, we can do that. We've talked about a constant, at least a positive b, like 2. To any power, we've worked these out, and it's defined no matter what the power is. And so we get a graph that looks like this. So it has some interesting characteristics that we may look at in a little bit. We will look at in a little bit more in the future. But now when we do it this way, we don't name it after the shape of the graph. See, back over here, we name the type of function after the shape of the graph. The graph's a line, so it's called a linear function. Over here, we name it after the formula. The formula in this case is y equals 7 times 2 to the x. Where's the variable? The variable is in the exponent, so this is called an exponential function. So it's the fact that the variable's in the exponent is why we name it an exponential function. So basically this type is named after the form of the formula, whereas linear, it was named after the form of the graph. Okay, so let me hide a few things here. And I want to go back here and hide a few things and do one more comparison. One more thing is that we found over here is that we could have started, if this didn't have a 0th term, we might have rather have written it this way on this second one here. Okay, where we would see that that the number of 2's that we're adding together is 1 less than the, well, if we started with 9 and then added 2 each time, thinking we're starting with that first term, then the number of 2's we're adding is 1 less than the term number. Or, if we don't want to think of it that way, just think of it this way. We can center this up at any particular point. This is called the point slope formula. So the number in the front is still the slope, no matter what we have here. But then we sort of shift it over. So if we shift over the x, we have to shift up the y to compensate, and it works out just fine. So for example here, let's look at this point 823. If that's the point we know, we could write it as 2 times parentheses x minus 8, comma, close parentheses, plus 23. Now look what happens here is we plug in 8 for x. 8 minus 8 is 0 times 2 is 0 plus 23 is 23. So sure enough, it goes through the point 823. And then this in front is the slope. So if we just know a point and a slope, we can find the equation of the line. And so in fact, we can write this over here. We can write it in a point slope formula where it goes to the point x1, y1, and we would write this as y equals m x minus x1 plus y1. Well, what do you think we're going to do over here? We can do a very similar thing. We can have a point base formula. Okay, so this one in the front, instead of becoming y0, just becomes y1, and the power is x minus x1. Let's check it out. Notice that if you put in x1 for x, you get x1 minus x1 is 0 for the power. B to the 0 power is 1 times y1 is y1. So sure enough, it goes through the point x1, y1, and then the base b is still how much we multiply each time to get the next one. So we should be able to go over here and have a point base formula for any particular point that we want. So for example, it's the exact same graph. All of these green formulas are the same exact relationship. Okay, it's when everything's said and done, it's the same function. So what we've got here is, let's take the point 356 for example. Then that's y equals 56 times 2 to the power x minus 3. Now these things are particularly useful whenever the initial thing 0, 7 or 0 whatever doesn't really make sense in the context of the problem, or it's not something that we know. For example, if we might see a function written this way. For example, on a linear we might say y equals some slope of, let's say, 3 x minus 2000. Okay, so maybe x is the year number, and so we might know that, and then say plus, and let's give it a number, let's say 157. So what this says is that in the year 2000 there were 157, whatever y represents, and it's going up by 3 each year. And so in this case it might make more sense to write the formula that way than it would be to, sort of figure out the slope y-intercept form, which is totally fine. You could do it that way, but the y-intercept might not really make sense because this formula might not apply at the year 0. Actually, there really wasn't even a year 0. It goes from 1 BCE to 1 CE, so it makes a difference. Likewise, we might write something like this, 5.3 times 1.05 to the x minus 2000. So then, again, x might be the year number, then x minus 2000 is how many years since the year 2000, and then we can see the base. We're going to see a little bit later on that this 1.05 means that it's going up by 5% each year. And it says that in the year 2000, the value was 5.3, whatever the appropriate units are for y. So, sometimes we like to have a point base formula, and there is a point base formula for every one. Okay, that's a pretty good introduction to sequences. Let's do a really quick overview, really fast, of some graphing. And remember that the y-coordinate of the y-intercept is given by y0, and that's going to just be a vertical shift. Okay? And this is the slope, which is how much we're adding when we go to the right one. And since it's the constant slope, this is giving me a straight line. As we go to the right, we're going up if the slope is positive, like that. If the slope is 0, we get a horizontal line. Okay, and if the slope is negative, then we get a decreasing function. Okay, we're going to do a really quick look at the graph, and then we may come back and talk about the graph more in a later time. But let's look at the graph over here of an exponential function. Now I've given multiple forms here, but let's pay attention right now to this one right here. And let's start with just a real basic one where y sub 0 is 1. Let me see if I can get this to 1 or close to it. There we go, it's at 1. So now notice if it's, so now we're talking about a real basic power function, an exponential function. And let's compare and contrast that exponential function with another. We've kind of compared and contrasted with linear functions. Now let's compare and contrast with power functions. And let's just do a real basic case where there's no transformations, a one step. So a one-step power function would be x to the n power. And an exponential function, it would be b to the x power. Now notice these are both just a one-step thing. They both just have a base and an exponent. So in that case, they're very similar to each other. But we can also think of it as there's a difference. And the difference is what these letters stand for. X is the input both cases, and x is the variable. So notice this is a variable base and a constant power on the power function. Whereas the which one's a constant, which one's a variable are exactly switched for exponential. In exponential we have a constant base and we have a variable exponent. So let's do an example. One of our good old examples we've looked at many times is y equals x squared for a power function. And over here, we might do y equals 2 to the x power. So once you pick a specific b, that's fixed. It's the x and y that change. And just like on the left side on the power function, once you pick a specific n, that's fixed. The 2 is fixed, and we change x and y. Now we have various shapes over here. We actually had 11 different ones, depending on what n was, determines the shape. Over here we really basically have just one shape or two shapes. Okay? And let's take a look at this picture and see that what we come up with. So I'm going to have one of these with this coefficient is 1. Then we're back to this one-step function where it's just y equals x to the b. And so we're going to see what the graph looks like there. And so here you can see. And notice that the bigger the b gets, the more pronounced the concavity is. And notice, though, that as we go way out here to the left, look what happens. It's approaching the x-axis. Now, it really doesn't matter. We're talking about a base bigger than 1. The bigger that base gets, the longer and tighter it stays to the axis here, or if you're going from right to left, the faster it approaches the axis. But also to the right, the faster this thing grows. So notice that exponential growth starts out very slowly, but then picks up speed and gets faster and faster and faster and faster, and eventually is extremely fast growth. We want to be careful because some people have a tendency to misuse the terminology, and they'll say, okay, well, this is growing really fast. It's exponential growth. Well, exponential growth is a very specific kind of growth. It's a growth at a constant percentage rate. It's a growth where you're multiplying by the same number each time. And this base here is what we're multiplying by as we move to the right or left. Okay? So here I'm going, let's see, let me put it on, let me see if I can put it on 2, for example. That would be the example that we were looking at. I can get 1.99 or 2.01. Let's pretend that's 2. Okay? And that's this function that we were looking at here, y equals 2 to the x power. Okay? And so notice, what do you see? You see 0, 0, 0, 1. Then when you get to 1, you get whatever the base is, 2. And 2, you get 4. And 3, it'll go to 8. And 4 to 16, and so forth. It gets off the screen there. What about negatives? Put in -1, it goes to -1/2. -2, 1/4. -3, 1/8. -4, 1/16, and so forth. And you can see it's getting closer and closer to 0 as we go out to the left. So it has a horizontal asymptote on the left and no asymptote on the right. It increases without bound going up. So if you look at this, the domain is all reals, and it is increasing concave up everywhere. And the range is 0 to infinity, not including 0. And this will be true for any of the positive bases. Now look what happens when I let the base be 1. Okay, so now these are still positive, but down close to 1. Okay. Okay, and if we let that base get down, if we let the base be equal to 1, then we just have 1 times 1 to the x. Well, 1 to the x is 1 no matter what x is, and so that just boils down to y equals 1, which is perfectly fine, but it's not really exponential anymore. It's really just a horizontal line. So we're not going to allow the base to be 1. But something interesting happens when you let the base be negative. Okay, so like there, it's -1/2. Okay, let me pull up Graphmatica for a minute, and let's graph a couple of things. Y equals 2 to the power x, the one we just looked at. Okay, you can see some key points. Well, what's going to happen if I make this replace the x by -x? You know what this is going to do to a graph. Okay, when you replace x by -x, it reflects over the y-axis, so it's going to look like this. Okay, but 2 to the -x is 1 over 2 to the x, which is 1/2 to the x. So this is going to be the same thing as if I wrote it as y. You'll see a color change here. Equals 1/2 to the power x. It's the same graph. You saw a graph's on top of it. The other one. So the green and the red one are the same graph. So what do we notice back over here is that when we have negative powers, they all look kind of like this. What do they have? They have, they're decreasing concave up. Now the asymptote is on the right side. It's still the x-axis is the asymptote on this basic setup here. Still goes through 0, 1 if that coefficient is 1. Okay? And we can get this to work out this way. Okay? So what about if the base is negative? Well, if the base is negative, we have a problem, because then we got negative to all these different powers. Okay? And when we have a negative to a power, we have problems, because if you remember, negatives to some powers were defined, negatives to other powers were undefined. If we try to let the base be a negative, then raise it to just any power, then we're going to have a function that's just full of holes. And we just don't want to mess with that. So we're not going to allow that. So actually, whereas we had 11 basic shapes over here for different powers for the power functions, really only have 2 shapes for a basic thing here. If we have y equals b to the x and b is greater than 1, it's going to look like this. Here's our axis. It's going to have x-axis horizontal asymptote on the right, on the left, I'm sorry, and goes over here to the right, increasing concave up, and it goes through 0, 1. On the other hand, if we have the y equals b to the x, and b is well, between 0 and 1, not including 1, then it's going to come down, hit the axis at 0, 1, and then come down to horizontal asymptote on the right. So the one on the right is called exponential increase or exponential growth. The one on the left is exponential decrease or exponential decay. So the right is appreciation, the left is depreciation. Okay? And really those are our only two basic shapes for just y equals b to the x power. We're not going to allow b to be 1 because that's boring. And we're not going to allow b to be negative or 0 because that gives us too many holes to be worth looking at. So we're just not going to use those. Okay? So I think that gives you a pretty decent overview. Going back, reviewing arithmetic sequences, talking about geometric sequences. We could see how we derived a formula. Okay? And I think that'll get us started on this unit. So hopefully that will give us a good introduction, and we can proceed from there a little bit later on as we go.